where that video left off. I won't be able to go back over that and do the material again. We have to move a little bit fast, especially if we want to talk about quantum information processing in this class. So, did you get a chance to watch the YouTube videos?
Yes.
Yeah. Were they clear? Were you able to see them and see what was going on?
Yeah, I think so.
Yeah.
Although there's like sometimes you were writing on the other dashboard and
Yeah.
there's so many dashboards.
It was still stuck
Yeah.
on this one? Yeah, okay. I think eventually it swings over though, right? Sometimes. Okay. Hopefully this one is better. So anyway, I have your graded homeworks here. I think I returned most of them the last time. Maybe just a couple. Homework 3. How? Not here. How. Mostly how. Okay. Rest of you should have gotten your homeworks back, right? From homework 3. I'm still grading homework 4. Okay, so before March meeting, during March meeting week, your assignment was to look at the videos for Vigner Weiskopf theory. So I will just quickly recall the result. That is that the atom field interaction in the rotating wave approximation was given by h bar omega plus summation over j so those are just the atom Hamiltonian, the field Hamiltonian, and then we had the interaction Hamiltonian, sum over j, h bar. Now I'm going to write that as gj, which is the interaction between the field and the vacuum, between the vacuum component of the electromagnetic field and the dipole moment of the atom. So this is just a rewriting of that Hamiltonian. And what you saw in the video was that if we now specialize to the initial state, that psi of 0 is equal to the system starting out in the state, the excited state 2, and then the ground state, and the atom and the electromagnetic field is in the vacuum state. You showed that the atom decays from the state 2, right, to at some time t. It has a description which is given by the decay of the atom. So finally, the atom finally at long times becomes a product between the atom in the ground state and a sum over all of the outgoing wave packets for the atom, for the photon in this state. And you can actually as I showed in this in the video, that you can actually then do this sum over the outgoing photon wave packet and show that it really looks like a spherical outgoing wave packet with some time dependence. So that is really sort of like shows you what a single photon wave packet looks like once you do this integral, right? So that was what I showed in that earlier lecture. And of course we also derived that gamma, this gamma which is the decay time for the atom, which is governed by the traditional Fermi's, which looks just like the original derivation you did for Fermi's golden rule. So you can see that this looks just like the decay for that you have to derive for Fermi's golden rule, where a atom interacts with some continuum of modes, and that also in the video I showed that this is just given by this formula, right? So that is the spontaneous emission rate in free space, or which is also the Einstein's A coefficient, if you're familiar with that from, say, undergraduate, when you talk about things like spontaneous emissions, stimulated emission, and so on. This is just the decay rate for an atom spontaneously emitting in free space. Also, we discussed the Purcell effect. Again, this is all just, I'm just reminding you, hopefully, of what you saw. So, what we said was, now, of course, if the sum over all the modes is assuming that you are emitting into free space. But what if, instead of free space, you have changed the boundary or the region around the atom, okay? Such that in this, for the atom, there is no modes, it's not a continuum of modes that it's emitting into, but only one single mode. How can you do that? Of course, is by creating a cavity, a boundary condition around the atom, such that only one electromagnetic mode can exist in that boundary condition, right? And when you do that, then we showed that the gamma cavity, so the cavity has some, cavity with, say, mode volume V, and with some spectral bandwidth delta nu half, because maybe the cavity, of course, in the ideal situation, the cavity is perfect and there is no decay of this cavity to any other modes, but more likely the walls of the cavity might absorb or something like that, and so you might get some bandwidth to the cavity, in which case we showed that the emission rate is approximately given by gamma cavity, given by phi mu over h bar epsilon naught q over v, where q now is the q factor of the cavity as defined by this, the quality factor. The cavity is defined by this equation, and this implies that the Purcell factor, which is given by the ratio between the gamma of the cavity and the gamma in free space, which is spontaneous emission, is equal to 3 lambda cubed over 4 pi squared q over. Okay. So this is a lot of very interesting results, right, that we have now derived, which shows that you can modify the rate at which an atom emits into photons by surrounding it with some cavity, and that all comes, of course, from this equation for the spontaneous emission rate. So it could have been derived even using Fermi's golden rule, but now we're going to see what happens as we, in fact, increase the Purcell factor to a level where the interaction G with the single photon mode. So now imagine that this cavity can only support one mode, right? That's what we have assumed. There's just one mode which is resonant. With atom, and in the deriving of the Purcell effect, I assume that mode has some bandwidth delta nu half. So now we can go to a limit where, in fact, that one mode is the only thing that exists in the world. Okay, and then we can also ask what happens when Gj, the interaction between the atom, which of course you know Gj comes from the interaction of the atom mu with the electromagnetic field of a single photon, which, I'm not writing the formulas again, but we know exactly how that goes. So when that interaction strength becomes much stronger than the decay rate of the atom into any other modes, or like in this case, when the Purcell factor is very large, essentially, that means that now the atom and the cavity are strongly coupled, and we can go away from the sort of sum over all modes to just considering one mode of the atom and the cavity interacting with each other. And this is a very important model in quantum optics, especially for quantum information processing. Okay? This is called the strong coupling regime. But before I go on, any questions about this part? This is the physics of it. Of course, the mathematics, I've tried to put it into that video so that you can watch it and look at it a couple times if you don't understand the mathematics. That should have been described, I think, in the video. But this is just the physics part of it, which you should always know, how it works. Okay. Any questions about this part? Okay, so we will now move to that case where the atom and the cavity are strongly interacting, which is called the strong coupling regime, where this G, the interaction strength, is much stronger than the decay of the atom into free space. So now this whole interaction, which I had written as a sum over J, can be simply written for just one mode, right? So once again I write that Hamiltonian in h bar omega to 2 plus h bar nu a dagger a. Now this is just one term. It's not a sum over J because there's just one mode in the cavity. Okay, so there's just one mode. So I should tell you what this model is called. It's called, sorry, I call this the James Cumming model, named after the scientist who first studied what happens in this model. Okay? And to simplify matters, we're going to start at time 0 now, okay, with the atom in the state 2, once again, just as before, and the photons in the state n. Okay? Then the effect of this Hamiltonian on this state is easily calculated. It's just h bar nu n plus half minus h bar plus h bar omega times n 2 n minus h bar g, and now the effect of the term due to a and a dagger. Remember, a acting on n is equal to square root n minus 1, and a dagger acting on n is square root n plus 1. Okay, so because of that, I get a term square root n plus 1 acting on the state n 2. Okay. So, state 1 and n plus 1, of course. And similarly, you see that therefore the state 2 comma n is coupled to the state 1 comma n plus 1. Makes sense. It goes from state 2 to state 1, emits a photon into the mode n, so you get n plus 1. So we should now also consider the dynamics of the state n1 comma n plus 1, and it's easy to show that that must be n plus 1 plus half. So I'm going to drop these halves because they're just going to keep appearing everywhere, right? So just write h bar n plus 1 So you can just renormalize the energy to get rid of that term. Times 1 comma n plus 1 minus h bar g square root n plus 1 times 2 comma. Okay. So we notice that the state 2 comma n and 1 comma n plus 1 are just coupled to each other, okay, and not coupled to any other terms because of this Hamiltonian, which is linear in the A and A diagram, which means that the entire space of all the possible field modes, right? The field modes could be anywhere from 0, 1, 2, 3 up to n, right? But what we're saying is, if we start in say the state 2 comma n, we are only coupled to 1 comma n plus 1, and they form like a little two-level system which is existing in this Hilbert space. So we can write the entire Hamiltonian H as a sum over all possible such Hamiltonians Hn, which only couple the states, 2 comma n and 1 comma n plus 1. So H then is equal to a sum over all n of Hn, okay, where this Hn now is simply h bar nu n, h bar nu times 1 0 0 1 minus h bar 0. I guess I took over 2 over here, 2g times square root n plus 1, okay, and 2g square root n plus 1 times 2 delta, where delta is equal to, you know what I'm going to do? Sorry, I didn't take off. Let's get rid of this 2. Where delta, of course, is nu minus omega, is the detuning between the atom and the field. Okay. So this looks a lot like, as I said, like a two-level atom, right? And the two-level atoms equations are very easy. We've already solved them many times. For when it's driven by this Rabi frequency, which I call Gn now, which is equal to G times square root n plus 1. And G, remember, or G naught, whatever you want to, maybe I should have written it as G naught. G naught is the, okay, just add a G naught everywhere. So to distinguish that, that is the vacuum Rabi frequency that we have seen many times over before. Okay. So that is for when n equal to 0, Gn will be equal to G naught, and that is the vacuum Rabi frequency that we have seen in many different situations before. So we can diagonalize this Hamiltonian very easily, right? So define now the effective Rabi frequency once again, which is dependent on both the detuning and the Rabi frequency, which is the due to the interaction of the atom with the nth photon state, basically. Okay. And the eigenvalues E, n will be just h bar nu n plus or minus h bar omega n. Okay. Which we can write out even more explicitly. There are two terms. There is the A and the B terms, if you like, okay, which is going to be h bar nu n. Now I have expanded out the detuning and so on in terms of this of these terms here. So h bar omega the B term is h bar nu n plus 1 minus plus 0 plus h bar over 2 omega m minus delta. Okay. So the delta, remember, has nu minus omega, and that will accordingly come into play over here. Okay. And the eigenvectors, okay, so this is going to be a complicated expression. I don't know that I need to bother writing it all out. It's basically just obtained by diagonalizing that matrix. So I won't write it out. Okay. We will just consider now, let's say, one situation, blue detune, right? So just as we could have the detuning of a classical laser field, which was blue detune from our two-level atom, we can also have a detuning between the cavity and the atom, which is, say, blue detune, which is that the cavity is at a higher frequency than the atom. Okay? So in that situation, we can make, and let's say it's far off resonance. Okay? So far off resonant cavity. Okay, which is with delta, and this is blue detune with blue detune. So when delta is the largest frequency in the problem, which is much greater than the, say, the Rabi frequency, okay, so let's say that that is true, then we can expand out and we obtain that EAN is approximately h bar nu n minus h bar times g squared n plus 1 divided by delta. So this should remind you of when we had the two-level atom which was being interacted with a blue detune field. One of the states is pushed down in energy by omega squared over delta, right? Where omega now is the effective Rabi frequency omega n given by this square root delta squared plus gn, and g squared times n plus 1 is of course just the interaction of the atom with the Rabi, with the nth photon in the field. Okay. Similarly, we can have E b comma n is approximately h bar nu n plus 1 minus or plus h bar g squared n plus 1 over delta, and correspondingly, without telling you like all the details of the math, this a comma n is approximately, okay, some normalization factor which I'm not writing down, times g times square root n plus 1 over delta times 1 comma n plus 1 plus a term which is 2 comma n. So you see that when delta is the largest frequency in the problem, a comma n is approximately 2 comma n. And similarly, you can show but quite easily that b comma n will be approximately 1 comma n plus 1, except with some factors, which is a little admixture of omega over delta with 2 comma n, or gn comma divided by delta times 2 comma n, okay, with a minus sign. Okay. So what does all this mean? Well, in the blue detune limit, as you can see, a comma n approaches the state 2 comma n, and b comma n approaches the state 1 comma n plus 1. Okay, and with their energies are similarly approaching e comma 2 comma n and e 1 comma n plus 1, as you can see right here. Right, this is the energy of the state with I should have plus h bar omega. Right. So this is like, so if I had written down, and I'll draw this in a little bit more detail, but 1 comma n plus 1, the state, and the state 2 comma n, right? As you can see, they are separated by the energy of h bar nu minus h bar omega, right? If this state is h bar nu n plus h bar nu, This one is h bar nu n plus h bar omega. Okay? So the splitting between them is delta, right? Which is equal to nu minus omega. Okay? And the interaction between them, right? Or there is this extra energy splitting, which you can think of as the this effective start shift. So this is delta plus, or maybe I should write it over here. This splitting is delta plus this h bar g squared n plus 1 over delta, which is the AC start shift. Okay, there's a factor. Okay, so it looks like the AC start shift because it goes as the Rabi frequency divided a square of the Rabi frequency divided by the detuning, and of course there is a splitting because of the fact that even without that interaction, you would have a splitting between these two states, which is given by the detuning between the cavity and the atomic state. Okay, so this is the if you now look at it from the viewpoint of the atom, right? So there's a cavity which is far off resonance. Okay. So to some approximation, you can say, well, the cavity doesn't exist. The cavity is just far off resonant from it. But yet, in fact, as you can see, the fact that the cavity is there, even if it is far off resonant, this state over here has been shifted. So E A comma n plus 1 minus E B comma n is approximately h bar omega minus h bar 2 times g squared n plus 1 divided by delta. Okay? So this is just like the start shift for the atom when the cavity is far off resonant, except that the cavity resonance has, or the atomic resonance has been shifted by this g squared n plus 1 divided by delta. Okay? But you could also conversely look at it the other way, which is that the photonic mode has been shifted by a slightly different energy, which is AEA. So this is atomic energy difference. Right? The atomic energy difference due to the presence of one photon is effectively just this shift in the atomic energy. Okay, so that's a AC start shift. Very similar to the AC start shift that you saw when the atom was being addressed by a classical laser beam. Okay? But now we can also look at it as impact of the atom on the cavity. And to do that, now we imagine that the atom doesn't even change its state. So it stays in the state A, but the photonic mode changes in its number of photons. Okay? So this is the energy required to add one photon to the mode when the atom is in either the A state or the B state. And remember, once again, the A state is close to the state 2 and the B state is close to the state 1. Right? So, okay, once again, you can show that this is approximately h nu minus h bar g squared over delta. And this is again valid when the atom is nearly in the state 2. Okay? And similarly, you can find AB n plus 1, or ABN, sorry, minus EB n minus 1, right, is approximately h nu plus h bar g squared over delta. Okay? So this is very interesting because when you think about it, if you wanted to add one more photon into the cavity, let's say imagine you sent in some laser or something that added some photons to the cavity, what it's saying is you couldn't send that atom or that photon in at the same frequency that you would have had if the atom was not present. right? So the effect of the atom being in state A, which is say close to the state 2, is to shift the frequency of the photon. Okay? So what could this be used for? Well, what this allows us to do, notice that the state of the atom does not change in this energy difference. Right? I have taken the same state 2 for the atom, and I've just added one photon to the cavity, and that has changed the frequency of the photon that I need. Which means by monitoring the frequency, I can tell whether the atom was in this state or in this state, without changing the state. Right? Without changing, because they come in also with opposite signs. Right? So without changing the state of the atom, I can actually tell what state it was in. This is called a non-destructive measurement. Okay? It's a non-demolition measurement, as we call it. Because most measurements, when you think about it, right, what they do is, for example, suppose I want to tell if an atom is in state 1 or state 2. Okay? What do I have to do to it? Well, typically what I'll do is, maybe I will send it into a detector, which explicitly, tries to figure out whether you're in state 1 or 2. For example, maybe it scatters some photons off of that atom, okay, which typically will cause the atom to transition from the state 1 to some other state, okay, or state 2 to some other state. Okay, and that, as an example, I may have atom in state 1 and 2, and then I might shine a laser on it to some other state 3, from which I can monitor, say, fluorescence or something like that. So typically I'll destroy the initial state 1 of the atom. Now of course when I make a measurement, I'm projecting the system into that state, right? That's quantum mechanics. I will of course find, let's say that I find the atom is in state 1, now the atom will be in state 1, that's a destructive measurement on, say, the state psi. Let's say the state psi was A1 plus B2. Right? There's a superposition of the atom in states 1 and 2. When I measure it with a photon, and let's say I find the frequency shift, has gone up by like this h bar g squared over delta, that means that now this atom is in state 2. Okay? So the original superposition of the atomic state is now projected onto state 2. Okay? So that, of course, it destroys this quantum state. But if I initially started in the state 2, okay, I don't need to modify the system. Okay? So this is a true, what we might call, non-destructive measurement, because the atom is still available there for me to keep interrogating. Okay? So this is what I mean by this non-destructive or non-demolition measurement. So this is a non-demolition measurement or dispersive measurement. Okay. And this idea of like interacting or probing the state of the atom, interacting with the cavity, such that when there's a shift in the state of in the frequency of the photon, depending on the state of the atom, this is of course very difficult, right? To achieve this limit is very difficult, because you need that the atom G, the G of the atom has to be much stronger of this atomic and photonic interaction. Atom-photon interaction G has to be much stronger than any of the other decays in the system. Okay? There can be no other decay rate that is as strong as this G. Okay? But once you have that, by blue detuning your photon or your laser, for example, we find that we can get a shift in the frequency of that photon, depending on whether this atom is in the state 1 or in the state 2 or in the state 1. And this method of doing this has been very successfully realized with superconducting qubits. Okay? Also with so-called these Rydberg atoms that have been enclosed in microwave cavities, that's also been successfully done. That was done by the group of Serge Haroche, for which they won the Nobel Prize a few years ago. Okay? So this this whole field of like a strongly interacting atom with a cavity, with a single mode, of essentially a harmonic oscillator, right, effectively. We are now in this strong coupling regime, and this regime is also given the name of cavity quantum electrodynamics. Okay? So the Jaynes-Cumming model essentially is what we use when we discuss this field of cavity quantum electrodynamics. Okay? So, which will often be given, the name CQED. Okay? Cavity quantum electrodynamics, or when they apply it to superconducting qubits, they call it circuit quantum electrodynamics, which also still the C is still the same, except that now you're using superconducting circuits instead of cavities. Okay. Okay. So this is the very important sort of regime. The last thing I want to talk to you about is actually a more. We worked out the algebra, and algebra is of course important to make sure that everything is working right. But we should also look at the sort of a geometrical or a physical or a visual description, which is also very useful. Okay. For that, we simply have to look at the energy levels that are encapsulated in this Hamiltonian and think about what's going on quite carefully. Okay. So we've already seen that if I were to think about what's happening with this Hamiltonian, let's say I start in the state of the system in the state 0, maybe I should use the entire board. Let's say I start with the atom in the ground state and the electromagnetic field in the vacuum state. Then we know that there's an energy difference omega, h bar omega, which takes me up to the atom in the excited state and atom in the ground state, that's h bar v. Right now I added one photon to the system, so the energy has gone up by 1. And if I add one atom, atomic excitation, go from the state 1 to the state 2 by going with an atomic excitation, and the cavity remains in the state 0, that energy is h bar omega. Right? That's the atomic Hamiltonian part. So this detuning here is delta. In this case, it's a red detune, right? Nu is lesser than omega. And now I can go ahead and add another photon to the cavity, okay, nu, which brings me up to the second set of states, which is 1, 2, where atom remains in the state 2, photon is now in the state. Atom remains in the state 1, photon is in the state 2. And of course I can add now one photon also to this guy, right, which is also up by nu. And so that's going to also be detuned from this state over here, which is the state 1, 2 and 2, 1 are now close together in energy with this delta. Okay? And in this case, as I said, delta is lesser than 0, this is red detuning. And further, we already have the interaction between the atom and the photon, which is between these two, is just h bar g square root of n plus 1. Okay? So in this case, n is 0, so this is just square root h bar g naught. Sorry. In this case, the interaction between these two guys, that is the Rabi flopping between them, is just going to be h bar g square root of 2. And so on and so forth. Okay? So we see that just as I had earlier done I had done the Hamiltonian diagonalization by algebra, we saw that that the Hamiltonian clearly only affects these sort of pairs of states, but now you can see it sort of in this physical description why only these kind of states seem to pair up or matter in the whole description. Now of course if I included a spontaneous emission, this picture is going to change, right? Because now the state with say 2, 1, right, can only go down to the state with 1, 0, right? So that of course is going to create some disturbances to this ideal picture, which we will have to take into account in a full description of cavity QED. But I'm only going to tell you a little bit about like sort of the basics of that formalism. Okay. So once again, you can see why the diagonalization and all that works. But the first thing we can certainly say is when you are on resonance, when delta is exactly 0, then you truly get Rabi flopping, right? You get Rabi flopping between two states, right, which have this 2, 0 and let's say 1, 1 with a frequency which is given by h bar g naught. And then if you go to the next higher state, you will get a Rabi flopping with the square root of 2, h bar g times square root of 2. Another way you'll often see this represented is, now imagine that you have this kind of a system and you send in yet another field to weakly probe all of these splittings. Okay? Let's say, for example, you sent in some laser field which was at some frequency, let's say h bar nu, and you slowly sweep it across this set of transitions. Then what you should see is when delta is equal to 0, for example, because of this Rabi flopping frequency, you might see a spectrum, right, which is essentially split by h bar g naught, for example, okay, or g naught in frequency, okay. Because as you can see that when delta is 0 or close to 0, when you are almost on resonance, then the only remaining term in the Hamiltonian, right, is this h bar g naught in the off diagonal terms, right? So if you have the Hamiltonian 0, 0, when detuning is 0, and you're left with g naught, right, in the off diagonal terms, then clearly the eigenvalues e plus minus will be just plus or minus g, right? Okay. So the splitting of these states by, okay, I guess it's 2g naught. Okay. The splitting of these states by 2g naught, right, is a characteristic, of course, when you are in the strongly of a dress state, right? This dress state picture that we have seen before when we did the two-level atom which is interacting with the electromagnetic field with a classical laser. This looks just like that dress states, except now that the splitting here is governed by this single photon Rabi frequency G naught. Now the problem is sometimes there have been some experiments that were done which were not so carefully done, where what people did is so let's say they took a quantum dot or something, or a quantum well, and they coupled it to some cavity, let's say some external cavity, either an optical cavity or a DBR, which is a dielectric distributed Bragg reflector type cavity, and they took a quantum well. I can find out that reference. This actually was published in Science and later found to be not quite right. So, it's kind of an interesting thing. So people, what they did was, they took this quantum well and they put it in this DBR cavity, a distributed Bragg reflector, and they took a laser and they slowly scanned the laser across the resonance. And they observed the splitting. Okay? And of course, you can also monitor the splitting as a function of detuning. Right? It's easy enough to solve. If you put back the delta, then of course we get a picture for the dress states, which is, let's say that this is the energy En, then you're going to get that traditional, the usual splitting, right? If you plot this, remember from like our previous dress state calculation, you will see that there is a change in the splitting. If you like, you can be more careful. Here are the original undressed states, and then the dress states as they go through resonance will be exactly on resonance. The splitting will be h bar times Gn, or 2 times that. Okay, these factors of 2 are always easy to take care of by just redefining the Rabi frequencies, and then you see this sort of like this shift, right? With detuning. So this is delta over Gn in the x-axis. Okay, and that's the energy. So people, what they did was they just plotted the function, the splittings of the states that they were seeing, and they observed, oh, right on resonance, I'm getting this splitting between the two modes. This looks like the strong coupling regime, and they published that as I have reached strong coupling between the quantum well and the distributed Bragg reflector. The problem with this is, of course, if you took even regular refractive index shift due to, like, let's say that you have put in some quantum well which had a slightly different refractive index, then it turns out you can also get a splitting which does exactly this behavior. The true signature, so meaning like it's just classical, there's no quantumness, there's no strong coupling, and there was no way in that experiment that they should have reached strong coupling, simply because the decay rate of the cavity, that is the distributed Bragg reflector, and of the quantum well into like spontaneous emission or into other cavity modes was much, much greater than any kind of coupling energy between the quantum well and the distributed Bragg reflector. The true signature then, if you want to prove that this is due to strong coupling, is by observing that this Gn is equal to G naught times square root n plus 1. So what you have to do, you have to go to a higher excited state, and you have to show that that Rabi frequency splitting is, going as a square root behavior, for example. Or you have to observe some other truly non-classical things, such as, like, say, collapse and revival of the Rabi oscillations between the atom and the photon, which I will get to in the next. You can of course show vacuum Rabi oscillations. You can show, which is also obvious, I hope, from this treatment, which is, if you look at this state right here, what this is saying is, if I start with the atom in the state 2, n, right, then the 2, 0, sorry, so I prepare the atom in the excited state, but there's nothing in the photon, right? But I'm strongly coupled to a cavity. Your first reaction would be, if an atom is in an excited state, it should decay, right? If an atom is in an excited state, it should decay, go down to the ground state, and that's it. Instead, what this is saying is, when I'm in the excited state 2, 0, the atom is in excited state, there's no photon in the cavity, I will go to the state 1, 1, where, that is, the atom has gone down to the state 1, there's one photon in the cavity, but instead of that photon escaping, it's recaptured by the atom. And the atom goes back and oscillates again. Okay? Goes back to the state 2, 0. It's a very non-classical behavior. So if you can observe that instead, that of course is also going to be a proof that you have truly created a strong coupling regime between the atom and the photon. So this is called vacuum Rabi oscillations. This effect, say for n equal to 0, you get vacuum Rabi oscillations. Again, you can see this is all just a consequence of two-level atom driven by a field, except that now the field is just a single mode of a cavity, and it has just one photon or a few photons in it. That's enough to already give you all this very non-classical behavior, which is truly a signature of quantization of the electromagnetic field. So if you go back and you think about what are the signatures of electromagnetic field being quantized, it's kind of hard to find many, okay? For example, the anti-bunching of the photons when they come from a single photon emitter that we talked about, when the G2, the correlation function, goes to 0. That is, of course, a signature of a single photon and quantization of a single of the electromagnetic field. But it's not as nice as observing something like Rabi oscillations that's driven by having no photon in the cavity. Here you have a system, you prepared an atom, you prepared the vacuum state of the photons in the cavity, so there should be nothing. Nothing should happen. Either the atom should decay down to the ground state, or intuitive notion is, the atom should just decay down to the ground state. But because we have modified the environment of the atom, we have made the environment of the atom have only one mode, and that mode is strongly interacting with the atom, okay, and doesn't decay to other modes in the rest of the universe, we see that we can get this very non-classical behavior, which is a signature of quantization of the photons. And this has all been observed in experiments, and I'll give you some references maybe in your notes, which is that you can actually observe this Rabi oscillations of the atom, which has been prepared in this state 2, 0. It goes down to the state 1, 1 and comes back. It does this repeatedly until, of course, one of the atom or the photon decay into some mode that is not either, that is not coherently coupled through the Jaynes-Cummings model. Okay. So, any questions? Again, at this point, this I can do a lot of math and I can show you, all kinds of stuff. But I'm trying to focus just on the physics description. The math is, of course, a little bit. You have to use some of the same math that you did from your earlier discussion of dress states. And now I'm going to do one more case. Again, I'm going to skip a lot of the math and try to just give you intuitive results. Okay, and I can reserve some of the math for your notes instead. And of course, you can also simply solve these Hamiltonians with Mathematica or something and observe all the graphs for yourself. Like this graph over here is just pretty straightforward to find by just looking at it. So now remember, I prepared the system, let's say in the state 2, 0, or maybe 2, n, and then I observe what happens to the system after that. Which means I have to prepare the system somehow in a Fock state, right? The photon state has to be in a Fock state in this description over here. Or I have to prepare the system, the vacuum state is easy comparatively. You just don't do anything and the system remains in the vacuum state. But to observe any of these higher order sort of like splittings, h bar g times square root of 2, then you really have to do a little bit more careful studies. There's another very interesting effect, which again is a signature of this quantization, which is called the collapse and revival. Again, I'm not going to derive all the math for you. I'll give you some intuition for it. So as before, we prepare the system, okay, at time 0 in an atomic state, which is the excited state, okay, and then we prepare the field in a coherent state. That's easy, right? We just shine a laser where Cn of 0 is just the traditional state of the coherent state that we've seen before, right? That's our so this is just equivalent to atom being in the state A, field being in the state alpha. Okay? Okay, and we want to know what happens to this state. Well, you can write the solution. Again, it's going to be a superposition of many different frequencies, one for each of the n. Okay. And I've assumed the resonance here, so delta equal to 0. Again, factors of half, I sometimes, I'm not so careful with them, just redefine your Gravi frequency approximately. Okay. Okay, so this looks like a fairly complicated function, right? This is going to have, looks like it's going to have a lot of frequencies in it for each of the components of the coherent state. So it looks like it will be fairly hard to solve. And that is somewhat true, but we can actually make some very good analysis of the system by making the approximation that the system is almost in the state n bar, meaning it has some average, so if you look at the distribution of these coefficients, Cn of 0 squared, let's say, right? We're going to say that it is somewhat narrowly peaked at some n bar, okay, with some width which is given by delta n, okay, and this delta n is of course just simply square root of n bar, which is a Poisson distribution, okay. If you do this approximation, right, then everything here factors out quite easily. I mean, n goes to n bar, and n plus 1 also goes to n bar, so that part just factors out, and it remains in this sort of coherent state with some distribution, except that now the Rabi frequency is the only thing, that is this gnt over 2, when that's equal to, say, pi, that would be a a state where the atom goes from state 2 to state 1, and that Rabi frequency will be given by just simply 1 over G naught times square root of n bar. So basically taking G and T over 2 and setting it to say pi over 2, that will give you a Rabi oscillation, right? So that is simply 1 over alpha times G naught, okay? This is just like classical Rabi oscillation, except as you can see, now you have alpha, which is basically like the amplitude of the field that is governing the time scale of the Rabi oscillation. So if I rewrite this as alpha up here, which is like the amplitude of the field, alpha times G naught times tau Rabi must be equal to 1. Okay, maybe there's a pi here somewhere. Okay, but I'm also missing. Fine. You know, you can put all that. Fine. Okay. So that's the classical Rabi oscillations. Good. So we have recovered that. But what if we go beyond that? So of course that would require some sophisticated calculation, but we're just going to again get some intuition by looking at an expansion of that phase. This phase term over here in the cosine and the sine, we're going to expand it out. Okay? So to go beyond approximation, we look at the phase of that cosine term, which goes as phi n. That's equal to G naught times square root n plus 1 times t. Okay? And in our approximation now, what we are saying is, instead of just making n go to n bar in this phase, I'm going to make n go to n bar plus delta n. Okay? So this is approximately G naught times square root n bar plus delta n times t. Okay? Which is just expanded, under the binomial distribution. Take out the n bar and then expand this in a series, and that gives you 1 over n bar delta n divided by 2 n bar. Okay? Which is again, since delta n is on the order of square root of n bar, you can see that this term is going to at some point go back to, let's say, instead of being at pi, it's going to go to say 2 pi, for example. Okay? So for small times, then we are going to get Rabi oscillations, but as time gets larger and larger, over here, this extra term over here is going to affect the phase of this Rabi oscillation. Okay? So this excess phase, which is going to linearly change in time, which is delta phi n, is equal to G naught T delta n divided by square root n bar, factor of 2. Okay? So this basically is going to cause the Rabi oscillations to decay. Because what it means is that at some point when you would have expected the Rabi oscillation to be at a maximum, this extra term in the phase is going to make it go to a minimum. Okay? Or make it go to 0. Okay? And this, and of course, since there are many frequencies in this problem, you could think of this as like some random phase that is going to be added to your cosine. If your nice cosine is going to have a lot of randomly varying frequencies, and when those frequencies, or when the phase due to those frequencies becomes say pi, or on the order of 1 approximately, or pi, you're going to get a loss, a decay of your system. You can make all this much more, as I said, mathematically rigorous, but it doesn't really matter. We're going to say that there's a collapse time, G naught tau collapse, goes as delta n divided by 2 square root of n, is on the order of pi, and this implies tau collapse is approximately on the order of 1 over G. Okay? G naught, I guess. Wherever you see G here, write as G naught because we already took into account the n dependence. But we can also say, well, what happens when this collapse time goes on the order of 2 pi? Okay, when this phase, extra phase, gets on the order of 2 pi, you're going to get a revival. Okay? So, revival times will be when G naught out divided by 2 square root of n bar, okay, is implies that this tau revival is on the order of pi times alpha divided by G. Okay. So the behavior of this probability to be in the state 2, okay, with time, probability to be in the state 2, okay, P of 2, okay, is going to oscillate, right? And then start revival. Okay. Sorry, should of course never exceed 1. Okay. So the idea is that this collapse time is on the order of 1 over G. The Rabi oscillation time, which we derived over there, is on the order of 1 over G alpha, right? Where alpha is the laser intensity or the laser amplitude, and then there is a revival time on the order of alpha divided by G, okay, as we just saw. You can also ask what happens at some intermediate time between the collapse and the revival. Okay? But we can actually show, and I'm not going to do that, the algebraic steps, I'll give it to you in the notes, that is actually a very interesting state. So at times, tau on the order of tau revival divided by 2, you find that the state of the system is in the following state. 1 over root 2 times alpha plus 1 alpha minus, where these alpha plus and alpha minus are some superpositions of alpha at different phases. Okay, I'm just going to skip that. Let's say at like, or just some combinations of alpha e to the I gt square root of n bar plus alpha e to the minus I gt or square root of n bar with some coefficients a and b, and then alpha minus is the same thing, a times this minus b times. Okay? So we see that initially, remember, we started, I erased it, but initially the system was at psi of, or maybe I should write here, the initial state of the system, psi of 0, was atom in the excited state times field in a coherent state. After a time, which is given by tau revival over 2, the atom can no longer be written as a product of the excited state times the or the atom state times the field state. We will come to this in the quantum information processing, but you've already seen states like this, for example, in Bell states. Bell states are, say, states of 2 photons or 2 atoms, which are, say, up plus down, right? And that cannot be written as a product of the individual states of the atoms. Similarly, this cannot be written as a product of the state of the atom times the field. The atom and the field mode have become entangled. Okay? So we'll return to that in quantum information process. So this is a very interesting way to prepare, in fact, very interesting states of the field as well. Because as you can see, at a time, in fact, at a very special time, okay, which is compatible with this Weiger time, Gt equal to pi square root n bar divided by 2, when atom is in state 2, the field is now in the state E alpha plus, which is on the order of I alpha minus I alpha. Okay. So this just corresponds in the XP diagram in the quadrature of Q and P for the harmonic oscillator, right, or the field mode. Remember, we introduced these various states of a field on that diagram, the X and P basis, right? So of course, I alpha just rotates it by some complex number, not so important. Just this is I alpha, right? Okay, just a new complex number, alpha. And here is minus I alpha. Right? And the system now is in the state alpha plus, which is a superposition of I alpha and minus I alpha, which are separated by this distance. Okay, 2I alpha. This is referred to as a Schrodinger cat. The reason is because you have taken a system which had some classical state, which is alpha. We always think of alpha as like a classical state, and convert it to a state which is a superposition of alpha in 2 different places. That is X and P. X, for example, is over here and also over here. Right? So if you think about the position of the harmonic oscillator, the position is simultaneously here and here. Okay, that's what we would think of as a Schrodinger cat, which is both dead or alive. Okay. Alright, so that's beautiful. And in fact, people have seen these states. The problem, of course, is we did all this with a perfect picture of no decay, no decoherence, everything. And as soon as you introduce decay and decoherence, typically these states tend to decay very quickly. So it's quite hard to observe them, to create them, and to keep them in that state for very long. Okay. But it is a very beautiful sort of physics that has been observed now in practice, in experiments. Okay. Any questions about this? I know it went a little bit fast, but as I said, mainly I'm trying to give you a flavor of the physics of the cavity QED and all the beautiful things that have come out of it. There's a lot more you can do, and maybe we can assign some of those papers and stuff like that into the end of term project for reading, so that you can follow through some of the details and also some of the experiments that have observed these beautiful effects. You can, present some of them to the class, for example. Now that you have the basics. So what I want to do next is to talk about how to introduce decay. And normally this last part of the course, I would have treated the full master equation formalism in full detail for you and worked out lots of examples and so on. But because we want to talk about quantum information processing hopefully next week, I'm going to give you some of the notes. Again, treat mainly the physics here and give you handouts for the notes, similar to what we did with quantization of the electromagnetic magnetic field. You can read through the notes. Some of it is quite, mathematically very dense, but hopefully my notes will be clear enough that you can follow them. But let me then talk about the sort of the physics of these cavity QED, or in general physics of these open systems. Okay, so just to finish up then, to include decay, so if I want to include decay and truly study what happens to this sort of Schrodinger Cat state or any other kind of states that I create in cavity QED, we see that we have to include, so we have the atom, right? And we have, through the Jaynes-Cummings model, we have this coupling term G, right? Which we have derived many times now, or G naught, whatever you want to call it, which is the vacuum Rabi splitting, right? The vacuum Rabi oscillation frequency, or the vacuum Rabi splitting as it is called, okay? And then you have your cavity mode. This one mode that is strongly coupled to the atom, that's the one. So normally, if we are not including decay, this is all we have seen, and that's what we just treated as this treatment of Jaynes-Cummings model and the Jaynes-Cummings collapse and revival of this system. Okay, but now of course we know the atom may not be perfectly coupled just to that. It may be talking to the rest of the world through all the 4 pi continuum modes. Right? When you did Vigner Weiskopf theory, you saw that the atom is emitting into all 4 pi directions, and unless you work really, really hard, there will always be some decay into some of those 4 pi continuum modes. So there will be some decay gamma, which might be on the order of, which is the spontaneous emission rate, and similarly the cavity will decay from something that we call kappa into some external modes. External modes that live out in the rest of the world, or maybe the cavity walls are not perfect and they absorb a little bit, so therefore they will, the traditional way to think about this, here's a Fabry-Perot resonator, this is a confocal Fabry-Perot resonator. For those of you who know something about laser cavities, this is a confocal resonator, let's say, and then you have an atom which is sitting in the center, and now the atom can exchange with the mirrors on either side. They can exchange with some frequency, Rabi frequency G, with this with the mirrors of the Fabry-Perot cavity, or it can emit out into free space with gamma, right, out into the rest of the world with gamma, and these cavities may not be perfect. They may decay out into the external universe with some decay rate kappa. Here I took like a one-sided cavity where only one side of the cavity is decaying. We can easily include both sides decaying, for example. Okay? So this is like a sort of standard model that you can think about when you think about what happens in cavity QED. For superconducting qubits, the system looks a little bit different in terms of the construction. You may have a superconducting qubit which is sitting on a chip, which is surrounded by some three-dimensional aluminum box. And the aluminum box is going superconducting at low temperature, and therefore it also looks like a cavity. The electromagnetic field is completely reflected from this metal in this superconducting box of the cavity. The reason to go cold is when it becomes superconducting, that normally if you have a metal and you have electromagnetic waves that are incident on it, a perfect metal will reflect, but of course some metals are not perfect. Most metals are not perfect, and therefore there will be a little bit of resistance in the walls of the metal, and that will lead to dissipation heat, which is generated by the electromagnetic wave hitting the edges of the box that you have constructed around your superconducting qubit. So then what's going to happen is that you're going to lose energy. That's effectively like this kappa, right? Basically you're decaying into some thermal modes, heat inside the aluminum walls or something like that. And when you go superconducting, that effect goes way down because the superconductor behaves much more like a perfect metal, and therefore the resistance is almost zero, and now you have very little heat dissipation in the modes of in the metal walls, and that greatly increases this kappa. And of course, this kappa is related to, let's say the frequency by the Q factor of the cavity. That is the omega naught or nu, which is the cavity frequency, nu divided by Q. Okay, and gamma, of course, we saw was related to the dipole moment and the frequency of the cavity. So there is a factor that is often quoted, which is called the cooperativity, which will often show up, which is just G squared divided by kappa gamma. And we'll see how this factor comes about if we have some time when we consider the decay in the third cavity QED. But you can already see why it is coming about physically. We've already seen that Gravi oscillations or something happen on the scale of this G. So G squared is essentially like a probability for this thing to interact with its single mode, like is shown here. And then you have the decay rates kappa and gamma in the environment. So this kappa and gamma together, this whole factor cooperativity sort of summarizes everything that is happening in this cavity QED system. So if you want to evaluate whether you are in the strong or in the quantum regime, so to speak, or you want this to be greater than 1, okay, G squared over kappa gamma. And if you want to be truly in the strong coupling regime, then you want G to be the strongest term in the Hamiltonian. So you want G to be far, far greater than kappa or gamma. Okay? Or you can say G squared over kappa gamma must be much, much larger than 1, maybe on the order of, I think, at least 10, preferably 100 would be an ideal limit to be in. And it is usually extremely hard to achieve this, except in a few cases, such as in superconducting qubits and maybe 1 or 2 cases with atoms which are trapped in optical cavities. So this is a regime that everybody wants to be in, but it's kind of hard to realize experimentally. Okay, so I already talked now about the circuit cavity QED. So now we should talk about next how one can implement this decay in a formalism that you can use to calculate all of these amplitudes and these decay rates more rigorously. And what I'll do in the next class is to give you an overview of this idea of open systems, open quantum. This kind of system is called an open quantum system because basically you have two quantum systems that are closely interacting plus some other interactions with the environment, and these environments, and of course this is true even for an atom which is interacting with a vacuum. That's also an open quantum system. The atom can decay into any of n possible modes which are in the vacuum, and of course then the information or the entropy of the system will increase when the photon is, when the atom has decayed into a photon, because now the photon is spread out over all 4 pi modes, so the entropy of the system goes up, and that's like an open quantum system. In contrast, in a closed quantum system, all the information is preserved, and the system always, remains in sort of some kind of coherent superposition of all the possible qubits. Okay, so we will discuss these kind of systems in the next class. I guess the other people didn't come to take their homeworks. Hopefully they'll come next. Okay, thank you.